Hello there, and welcome to Sleepy Science Vault. What if you floated forever in space? Not sinking. Not falling in the way you understand falling. Just drifting. Endlessly. Suspended in a silence so complete it would swallow every sound you've ever known. It's a thought that visits almost everyone at some point. Late at night, staring up at a sky scattered with light older than human memory, the question rises quietly on its own. What would it actually feel like to let go? To release every tether, every rope, every certainty, and simply drift into the dark? Tonight, we're going to explore that question. Slowly. Carefully. Fact by fact. Not to frighten you, but to help you understand something vast and strange and beautiful, the true nature of space, and what it would really mean to float within it. Let your mind soften. There's no need to hold on to anything right now. Just listen, and let the universe unfold around you, one quiet truth at a time. So let's begin with the phrase itself. Floating forever. What does that actually mean? It sounds peaceful, doesn't it? Almost like lying on the surface of a still lake, weightless, arms outstretched, eyes closed, the world reduced to a gentle hush. But space is not a lake. And floating, in the way we imagine it, is not quite what happens out there. When people picture floating forever, they usually imagine something eternal and unchanging. A body suspended in perfect stillness, drifting endlessly through black velvet space, untouched by time. It's a haunting image. Almost meditative. But nature rarely allows for something so simple. Even in the vacuum of space, nothing truly stays still. Because here is the first quiet truth we need to sit with tonight. You would not stop moving on your own. If you were released from a spacecraft, drifting freely into space, your body would not simply hover in place like a feather suspended in still air. There is no still air. There is no resistance to slow you down, but there is also no anchor to hold you steady. Whatever motion you had at the moment you let go, you would keep. Forever. Or at least, until something else acted upon you. If you pushed off gently from a spacecraft wall, you would drift away at that same gentle speed, indefinitely. If you tumbled, even slightly, from an awkward push, you would keep tumbling. Slowly. Endlessly rotating through the dark, with no air resistance to calm the motion, and no ground to stop you. Your body becomes a wandering thing, governed only by the laws of motion, obeying a simple, ancient rule. An object in motion stays in motion, unless something interferes. It's a strange thought, isn't it? That stillness, true stillness, is almost impossible out there. And this brings us gently to our next truth. One that quietly reshapes everything we think we understand about floating in space. Floating forever is misleading, because gravity always changes your path. Even in the depths of space, gravity does not disappear. It weakens. It stretches thin across vast distances. But it never truly vanishes. Every planet, every star, every moon, every scattered fragment of cosmic debris, pulls gently on everything else. Even you. So if you were floating freely, far from any spacecraft, you would not be moving in a straight, endless line through the void. Not really. Your path would curve, ever so slightly, shaped by the gravity of nearby worlds. Perhaps it would curve toward the Earth beneath you. Perhaps toward the moon. Perhaps toward the sun itself, tugging softly across millions of miles. Floating forever, then, isn't a straight, empty drift into nothingness. It's a long, slow negotiation with gravity, an invisible hand nudging your path, one imperceptible degree at a time. Which leads us to something people often misunderstand completely. Floating in orbit doesn't mean gravity has disappeared. This one surprises a lot of people. When we watch astronauts drifting gently inside the International Space Station, weightless, hair floating, tools hovering beside them, it's easy to assume gravity has simply switched off. Like a light in an empty room. But that's not what's happening at all. At the altitude where the space station orbits, gravity is still almost as strong as it is here on the surface of the Earth. Astronauts are not escaping gravity. They are still very much within its grip. So then, why do they float? Because they are falling. Constantly. Which brings us to one of the most beautiful truths in all of orbital mechanics. Orbit is continuous falling. Picture the space station moving forward at incredible speed, thousands of miles per hour, while gravity pulls it downward, toward the Earth. It falls, and falls, and falls. But because it's moving forward so quickly, the curve of its fall matches the curve of the Earth itself. So instead of crashing into the surface, it falls around the planet. Forever circling. Forever falling. Never landing. That is what an orbit truly is. Not an escape from gravity, but an elegant, endless collaboration with it. A falling that never ends, gliding gently around the curve of a world. And inside that endless fall, everything feels weightless. Not because gravity has stopped, but because everything inside the spacecraft, astronaut and object alike, is falling together, at the exact same rate. There's nothing pressing you downward, because there's no ground to catch you. It's less like floating in emptiness, and more like being caught in a slow, graceful, infinite fall. Which brings us to something even stranger. Out there is no true up or down. On Earth, our sense of direction is anchored by gravity pulling us toward the ground. Up feels like up. Down feels like down. It's instinctive, automatic, something we rarely question. But in space, without a strong gravitational pull tugging you in one dominant direction, that instinct dissolves. Astronauts often describe a strange disorientation during their first days in orbit. Ceilings can feel like floors. Walls can feel like the sky. Without gravity anchoring their bodies, their inner sense of direction slowly unravels, and has to be relearned. Out in open space, drifting freely, this disorientation becomes even more profound. There would be no ceiling, no floor, no horizon to orient yourself against. Just an endless field of stars stretching in every direction, equally up and equally down, all at once. It's beautiful, and also deeply unsettling, if you let yourself imagine it too vividly. Which brings us to a colder, more sobering truth. If you drifted away from a spacecraft, rescue would become almost impossible. Space does not behave like the ocean. There are no currents to carry you back to shore. No air to slow your drifting. If you floated away from a ship, even slowly, even gently, you would continue moving in that direction, indefinitely, unless someone intervened. And in the vast scale of space, even a slow drift can carry you an unreachable distance within minutes. This is why astronauts performing spacewalks are always tethered. Always. A single loose grip, a single miscalculated push, and the distance between safety and endless isolation could open in seconds. It's a haunting thought. Not because space is cruel, but because it is simply, utterly indifferent. It does not pull you back. It does not slow you down. It only waits. Which leads us to the truth our bodies fear the most. Your body cannot survive long in a vacuum. Space is not simply empty. It is a vacuum, a region with almost no matter, no air, no pressure at all. And the human body is built for pressure. Built for oxygen. Built for a very particular, delicate balance that Earth provides so effortlessly, we rarely think about it. Exposed directly to a vacuum, the human body would face a rapid, brutal series of changes. Not an explosive one, like the movies often suggest, but something quieter, and in its own way, more unsettling. Because the very first danger wouldn't be the cold or the radiation. It would be the loss of oxygen. Oxygen loss becomes the first danger. Without a breathable atmosphere, unconsciousness would occur within about 15 seconds. The brain, so dependent on a steady, uninterrupted flow of oxygen, would begin shutting down almost immediately. Not with panic. Not with drama. Just a slow, quiet fading, like a light dimming in a room with no one left to notice. And beyond the loss of oxygen, more dangers wait in the dark. Because space exposes you to vacuum, radiation, and extreme temperatures, all at once. Without an atmosphere to shield you, harmful radiation from the sun and distant cosmic sources would reach your body directly. And without air to regulate warmth, temperatures could swing to unimaginable extremes, blistering heat in direct sunlight, and a deep, silent cold and shadow, colder than anything felt on Earth. Space is not gentle. It does not ease you into stillness the way our imagination often suggests. It is vast, and beautiful, and utterly unconcerned with whether you survive within it. And yet, understanding these dangers doesn't make space feel less wondrous. If anything, it makes the universe feel more astonishing. Because against all of this, against the vacuum, the cold, the radiation, the endless pull of gravity reshaping every path, we manage to build machines capable of carrying us there anyway. Fragile, breathing creatures, wrapped in metal and glass, drifting gently above a planet we call home. We've only just begun to understand what it truly means to exist beyond our world. In the next part of our journey, we'll drift further into this vast unknown, exploring what our bodies experience during real missions, how astronauts adapt to weightlessness, and just how strange, and quietly beautiful, survival among the stars can be. For now, let your thoughts settle. Let the stars above you feel a little closer, and a little more familiar. We'll continue soon. Let's continue drifting deeper into this thought experiment. Because so far, we've only looked at the raw dangers, the vacuum, the cold, the radiation, the silent fading of consciousness. But what if, just for a moment, we set those dangers aside? What if you could survive? Suppose your body were perfectly protected. Imagine, just as a thought experiment, that some advanced suit or shell shielded you completely. Full pressure. A steady, endless supply of oxygen. Perfect insulation against both the burning light of the sun and the deep cold of shadow. No radiation reaching your skin. No vacuum pulling the air from your lungs. In this imagined scenario, you wouldn't die. Not from the environment, anyway. You would simply continue drifting, existing. A small, living point of warmth, wrapped in protection, moving silently through the vast dark. It's a strange thing to picture. Because once the immediate physical dangers are removed, an entirely different set of truths begins to surface. Quieter ones. Slower ones. Truths less about the body, and more about the mind, and about time itself. Because if you were somehow preserved, truly preserved, your body could drift for an extraordinary length of time. With no atmosphere to create friction, and no ground to stop your motion, there would be nothing to slow you down. No air resistance tugging at your limbs. No surface to collide with, in the emptiness between stars. Your body, protected and drifting, could continue moving through space for what would feel, from a human perspective, essentially forever. Not because you would be traveling towards some destination, but because there would be nothing out there to stop you. It's a peaceful image, in a way. And also, if you sit with it long enough, a deeply lonely one. Because that leads us to something far heavier than any physical danger. Isolation and silence would become overwhelming. Try to imagine it honestly. No sound. Not the hum of an engine, not the whisper of wind, not even the quiet rhythm of your own footsteps against solid ground. Just silence. Total, absolute silence, stretching in every direction, forever. At first, perhaps, it might feel almost soothing. A kind of ultimate stillness. But minutes would turn into hours. Hours into days. And slowly, that stillness would begin to feel less like peace, and more like absence. An emptiness with no edges. No conversation to anchor your thoughts. No other voice to remind you that you are not, in fact, entirely alone in existence. Human minds are not built for that kind of isolation. We are wired, deeply and instinctively, for connection, for the presence of others, even in small, quiet ways. Remove that entirely, and the mind begins to search for something to hold on to. Memories. Imagine conversations. The sound of your own thoughts, growing louder simply because there is nothing else to listen to. Which brings us to a truth grounded not in science fiction, but in real, documented human experience. Chronic isolation affects mental health. We know this, not just intuitively, but from studies conducted right here on Earth. Long-duration astronauts, polar researchers stationed through months of endless winter darkness, even individuals in extended solitary confinement, all report similar patterns. Anxiety, disrupted sleep, difficulty concentrating. A kind of quiet emotional erosion that builds slowly over time. The mind craves stimulation, connection, and a sense of orientation within time itself. Strip all of that away completely, replace it with endless silence and unchanging stars, and even the calmest, most resilient person would eventually feel that absence begin to press inward. Gently, at first, and then, a little heavier. It's worth sitting with that thought for a moment. Not to feel afraid, but to appreciate, more deeply, the presence of sound, and voices, and other people in our lives back on Earth. The comfort of simply not being alone. And amid this profound silence, your body, meanwhile, would continue its quiet, uninterrupted motion. Because motion through space continues almost indefinitely. Without resistance to slow it down, whatever direction and speed you started with, you would keep. Drifting past scattered fragments of ancient rock. Past silent, distant planets. Past regions of space so empty, light itself might take years to cross them. It's a humbling image. A single figure, protected and drifting, moving endlessly through a universe far larger than the human mind can fully comprehend, carried forward by nothing more than the simple laws of motion, set in place the moment you first let go. Now, let's shift our attention for a while. Away from isolation and drifting, and let's imagine something a little more grounded. A little more human. Let's imagine what everyday life would actually look like, without gravity holding everything gently in place. Because gravity does far more than keep our feet on the ground. It shapes nearly every small, unnoticed detail of daily existence. And without it, even the simplest tasks transform into something strange, and often quietly beautiful. Let's begin with something as ordinary as objects floating. Objects float differently. Here on Earth, gravity gives us a shared, predictable sense of down. Drop a pen, and it falls, exactly the same way, every single time. But remove gravity, and that predictability dissolves completely. A pen released in midair doesn't fall, it simply stays there, suspended, drifting only if disturbed by the faintest breath of air or a light touch. Astronauts often describe this as one of the most surreal parts of adjusting to space. Tools set down for a moment quietly drift away. A notebook released mid-sentence hovers gently in place, as though waiting patiently to be picked up again. Nothing settles. Nothing rests. Everything exists in a kind of soft, perpetual suspension. And it's not just solid objects that behave this way. Liquids form blobs. Without gravity to pull liquid downward into a container, water behaves in an entirely different way. Released into open air, it doesn't splash, or pour, or spread flat. Instead, surface tension takes over completely, and the liquid gathers itself into a smooth, wobbling sphere. Perfectly rounded. Gently trembling. Almost like a slow-motion, floating droplet of glass. Astronauts have often played gently with this phenomenon, releasing small spheres of water inside the station, watching them drift, catching sunlight through the windows, refracting it into soft, shifting colors. A strange kind of beauty, born entirely from the absence of gravity. Even fire doesn't behave the way we expect. Flames become spherical. On Earth, gravity plays a quiet, essential role in shaping fire. Hot air rises, cooler air rushes in beneath it, and that constant circulation pulls flames into their familiar flickering, teardrop shape. Remove gravity, and that entire process disappears. Without rising heat to shape it, a flame in microgravity doesn't flicker or dance. It simply glows, softly, and almost perfectly round. A small, gentle sphere of blue-tinted light, quietly burning in place, without the usual crackle or movement we associate with fire. Calmer. Quieter. Strangely serene. And this absence of gravity doesn't just affect flames and liquids individually, it changes the way substances interact with each other entirely. Mixtures behave differently. On Earth, gravity helps separate substances of different densities. Oil rises above water. Heavier particles settle at the bottom of a container. But without gravity's steady pull, that natural separation disappears. Liquids and gases mix unpredictably, clinging together in strange formations, sometimes taking much longer to properly combine, or refusing to separate at all. This isn't just a curiosity. It's a genuine challenge for astronauts. From daily science experiments to simply making a proper cup of coffee, something as instinctive as stirring becomes an entirely new skill to relearn. And finally, even something as universally human as sleep transforms completely. Sleeping requires restraints. Without gravity gently pressing your body into a mattress, drifting off in open air is not only strange, it can be surprisingly disorienting. Left unrestrained, an astronaut's body will slowly drift throughout the sleeping area during the night, gently bumping into walls, or equipment, or simply floating in an unfamiliar position. To rest properly, astronauts sleep inside small, enclosed sleeping bags, gently strapped to the wall. Held in place, not by pressure, but by soft fabric and quiet stillness. In many ways, it becomes less like lying down to sleep, and more like being softly, gently held in place by the spacecraft itself, suspended in a peaceful, weightless stillness through the night. It's easy to forget how much of our ordinary human experience depends entirely on gravity. Something we rarely think about, quietly shaping nearly everything we do. Remove it, and the world we know reshapes itself into something delicate, strange, and unexpectedly beautiful. And this is only the beginning of what changes once gravity fades from the picture. In the next part of our journey, we'll continue exploring what it truly means to exist without gravity's gentle hold, how the body itself begins to change over time, and what long-duration life beyond Earth quietly reveals about the strength and fragility of being human. For now, let this stillness settle around you. Let your thoughts drift, slow and weightless, just a little longer. We'll continue soon. Let's continue drifting through this quiet exploration of a body suspended, away from gravity's familiar hold. Because even something as simple as drinking a glass of water becomes an entirely different task altogether. drinking becomes difficult. On Earth, we rarely think twice about taking a sip of water. Gravity does most of the work for us, pulling liquid down through the glass, into our mouths, without any real effort required. But in space, without that gentle pull, liquid doesn't flow the way we expect. Tip a cup, and the water won't pour out. It simply clings to the container, to itself, forming soft, wobbling shapes that drift rather than spill. This is why astronauts drink from sealed pouches instead of open cups, sipping through narrow straws, carefully controlling each small amount. Even something as instinctive as drinking requires a quiet kind of relearning, a gentle recalibration of habits built over an entire lifetime on solid ground. And once you begin to notice these small shifts, you start to notice how movement itself changes completely. Movement becomes push and glide. Walking, as we know it, simply doesn't exist without gravity. There's no ground to push against in the way our legs expect, no familiar resistance beneath each step. Instead, astronauts move by gently pushing off walls, handholds, and surfaces, gliding smoothly through open space, drifting from one point to another in slow, graceful arcs. It looks almost like a strange, quiet ballet. Careful, deliberate movements, each push calculated just enough to reach the next surface without tumbling out of control. Overshoot slightly, and you might drift past your destination entirely, gently spinning in place, waiting for something, anything, to grab hold of. It's less like walking through a room, and more like swimming through still, silent air. And it's this constant, delicate interaction with weightlessness that has taught scientists so much about how the human body actually works. Because scientists use microgravity for experiments. Certain physical processes, how flames burn, how liquids behave, how crystals form, how cells grow and divide, all become clearer, in strange and revealing ways, once gravity is removed from the equation. Without gravity's influence quietly shaping the outcome, researchers can observe the pure, underlying behavior of matter itself, free from the constant pull that shapes almost everything on Earth. This is part of why the International Space Station exists at all. Not merely as a marvel of engineering, floating quietly above our planet, but as a genuine laboratory. A place where curiosity can explore questions that simply cannot be answered anywhere else. And you don't need to travel all the way into orbit to experience a small taste of this weightlessness yourself. Because parabolic flights briefly recreate weightlessness. Specially designed aircraft can fly in long, sweeping arcs, climbing steeply, then curving downward in a carefully controlled freefall. For roughly 20 to 30 seconds at a time, everyone inside the aircraft experiences true weightlessness. Objects drift. Bodies float gently upward from their seats. For a few brief, surreal moments, it's as close as most people will ever come to floating, without ever leaving Earth's atmosphere at all. These flights are sometimes nicknamed, half-jokingly, the Vomit Comet, a playful name for an experience that is, in truth, remarkably close to a genuine, fleeting glimpse of space itself. But true, sustained weightlessness, the kind experienced over weeks and months aboard a spacecraft, affects the human body in far deeper, far more lasting ways. Because your body doesn't just adapt to weightlessness. It begins, quietly and gradually, to change. Let's start with something astronauts notice almost immediately, often within the very first day. Blood shifts toward the head. Here on Earth, gravity constantly pulls blood downward, toward our legs and lower body. It's such a normal, automatic process that we rarely think about it at all. But remove gravity, and that downward pull disappears. Blood that would normally settle in the lower body instead redistributes itself more evenly, shifting noticeably upward, toward the chest and the head. Astronauts often describe this sensation as feeling similar to hanging upside down, gently, for an extended period. A subtle pressure. A fullness, settling quietly behind the eyes and across the sinuses. It's not painful, exactly, but it is strange. A quiet, constant reminder that the body is adjusting to an entirely new internal balance. And this shifting fluid doesn't just create a feeling. It visibly changes the body's appearance. Which brings us to something both astronauts and scientists refer to, almost affectionately, as puffy face and skinny legs. With fluid shifting upward and away from the lower body, astronauts' faces often appear slightly swollen during the first days in space, rounder, fuller, sometimes even a little flushed. Meanwhile, their legs, no longer holding onto that same fluid, begin to appear noticeably thinner. Almost delicate, in a strange way. It's a visible, almost gentle reminder of just how deeply gravity shapes even the smallest details of our physical form, details so constant, so unchanging throughout our entire lives, that we rarely even notice them until they're gone. And this fluid shift doesn't just change appearance. It sets off a quiet chain reaction throughout the entire body, beginning with the kidneys. Because increased urination follows almost immediately. As fluid redistributes toward the upper body, the body's internal sensors interpret this shift as a sign of excess fluid overall, mistakenly believing there's simply too much fluid circulating throughout the system. In response, the body begins eliminating what it perceives as surplus, resulting in noticeably increased urination during the earliest days of adjusting to microgravity. It's the body doing exactly what it's designed to do, responding logically to new information. It simply doesn't yet understand that the extra fluid isn't extra at all, only differently distributed, in an environment its instincts were never designed to expect. And this process, over time, leads to something even more significant. Blood volume itself begins to decrease. As the body continues eliminating what it believes to be excess fluid, overall blood volume gradually drops, sometimes by a noticeable percentage within just the first few days. It's the body quietly recalibrating itself, adjusting internal fluid levels to match this strange, new weightless existence. This isn't dangerous, in itself. The body is remarkably adaptable. But it does mark the beginning of a much deeper, more complex transformation, one that reaches all the way into the rhythm of the heart itself. Because from here, the cardiovascular set point changes. On Earth, the heart works constantly against gravity, pumping blood upward, against a steady downward pull, especially toward the brain. It's a task so fundamental, so continuous, that the entire cardiovascular system evolves around it, strengthening itself specifically for that purpose. But in microgravity, that resistance disappears. And the body, sensing this shift, quietly begins to reset its internal baseline, establishing a new, lower normal, suited for an environment where gravity's downward pull no longer plays a role in circulation. Which brings us to a particularly fascinating, quietly profound truth. The heart no longer works against gravity. Muscles, including the heart itself, grow stronger through resistance, and weaker through prolonged rest. Without gravity constantly demanding extra effort from the cardiovascular system, the heart, over time, doesn't need to work quite as hard. And so, gradually, it begins to adapt. Sometimes growing slightly smaller, slightly less robust than it once was on Earth. It's a strange, almost poetic irony, isn't it? The very organ responsible for sustaining life, quietly softening, simply because the constant, invisible burden of gravity is no longer there to strengthen it. This is precisely why astronauts returning to Earth after long missions often feel profoundly weak, at first. Their hearts, and their entire cardiovascular systems, must slowly relearn how to work against gravity all over again. Something that felt effortless before their journey, now demands conscious, careful readjustment. There is something quietly moving about all of this, when you really sit with it. Our bodies aren't simply passive vessels, unaffected by the world around them. They are constantly listening, constantly adapting, shaped moment by the very forces surrounding them. Remove one of the most fundamental forces we've ever known, and the body responds, gently, faithfully, doing exactly what it was designed to do, adapt to whatever reality it finds itself in. And this is only the beginning of the body's long, quiet transformation. In the next part of our journey, we'll continue exploring just how deeply space reshapes the human body, from muscles and bones to balance and beyond, revealing, more and more, just how remarkable and how fragile our existence truly is. For now, let your breathing settle, slow and steady, and let your body rest here a little longer, weightless in thought, even as it remains gently held by gravity below you. We'll continue soon. Let's continue where we left off, following this quiet transformation, deeper into the body's long adjustment to a world without gravity. Because the heart's story doesn't end with simply working a little less. Over time, the heart muscle itself begins to shrink. Muscle, by its very nature, responds to demand. Use it constantly, against resistance, and it grows stronger, thicker, more capable. Remove that demand, and it begins, slowly, to soften. The heart is no exception. Studies of astronauts during long-duration missions have shown a measurable decrease in heart muscle mass over time, a quiet, gradual thinning, as the organ adjusts to a life where pumping blood no longer requires fighting against gravity's downward pull. It's not a dramatic change. Not something felt suddenly, or dangerously, in the moment. It happens slowly, the way a path through a forest fades, almost imperceptibly, when it's no longer walked each day. And within this general shrinking, one particular chamber draws special attention from researchers. Because the left ventricle becomes smaller. The left ventricle is, In many ways, the powerhouse of the heart, the chamber responsible for pushing oxygen-rich blood out to the rest of the body, including that long, demanding journey up against gravity, toward the brain. On Earth, this chamber works especially hard, shaped over a lifetime by that constant upward battle. In microgravity, with that resistance removed, the left ventricle doesn't need to generate the same forceful pressure. And so, gradually, it adapts, becoming slightly smaller, slightly less robust, mirroring the reduced demands placed upon it. It's a small, quiet echo of just how precisely our bodies calibrate themselves, always shaped by whatever environment surrounds them, whether we notice it or not. But the heart doesn't change alone. The very vessels carrying blood throughout the body begin shifting too. Because blood vessel function changes as well. Blood vessels are far from simple, passive tubes. They're active, responsive structures, constantly narrowing, widening, adjusting their tension to help regulate blood pressure and circulation throughout the body. On Earth, much of this careful regulation exists specifically to manage gravity's effects, ensuring blood reaches the brain properly, even when we stand suddenly, or move quickly from lying down to standing up. In space, without that gravitational challenge, blood vessels don't need to work quite as hard, or respond quite as dynamically. Over time, their walls can become slightly less elastic, slightly less responsive than they once were. A subtle shift, but a meaningful one, particularly once the body returns to Earth's demands once again. And this leads us to something particularly delicate, a system so precise, most of us never even realize it exists. Because blood pressure sensors become less sensitive over time. Nestled within the walls of our blood vessels are tiny structures called baroreceptors, quiet, constant sentinels, monitoring blood pressure moment to moment, sending rapid signals to the brain to adjust circulation as needed. It's this system that allows you to stand up quickly from a chair without fainting, instantly and invisibly compensating for gravity's sudden pull on your blood. In microgravity, with far less need for these dramatic, moment-to-moment adjustments, these sensors gradually become less responsive, less finely tuned. It's a quiet consequence of an environment that simply no longer demands the same vigilance. Which brings us to something broader still, a shift in the body's entire automatic control system. Because autonomic regulation itself begins to change. The autonomic nervous system operates quietly, constantly, entirely without conscious thought, regulating heart rate, blood pressure, digestion, and countless other essential processes in the background of our lives. It is, in many ways, the body's silent caretaker. In space, this caretaker must relearn its role. Many of the signals it once relied upon, particularly those related to gravity and fluid distribution, no longer arrive the same way. And so, gradually, the entire system recalibrates, adjusting itself to a new, weightless normal. It's a remarkable act of adaptation, when you really consider it. An entire regulatory network, refined over millions of years of evolution, quietly rewriting its own expectations, simply because the world around it has changed. Even the brain itself must adjust, in ways deeply tied to this quiet redistribution of fluid. Because brain blood flow regulation changes as well. Just as the fluid shift toward the head affects the face and sinuses, it also affects circulation within the brain itself. Under normal gravity, blood flow to the brain is carefully regulated, moment to moment, to maintain a steady, stable environment, crucial for something as delicate and vital as neural function. In microgravity, with blood distributed differently throughout the body, this regulation must adjust as well. Researchers continue to study these changes closely, exploring subtle shifts in brain structure and function during long-duration missions, a quiet reminder of just how deeply connected our minds are to the physical forces surrounding our bodies, even in ways we rarely consciously notice. And within the spacecraft itself, another quiet factor complicates this delicate balance. Because elevated carbon dioxide levels can worsen these effects. Aboard spacecraft, particularly during long missions, carbon dioxide levels are often slightly higher than what we're accustomed to breathing here on Earth. Life support systems work continuously to filter and manage air quality, but even small elevations in CO2 can subtly affect blood vessels, causing them to widen slightly, which can, in turn, intensify some of the fluid shifts and pressure changes already occurring within the body. It's a quiet layering effect, small changes building upon other small changes, each one shaping the body's ongoing story of adaptation, just a little further. And in response to these shifting conditions, particular structures within the body also begin to adjust. Because chemoreceptors themselves begin to adapt. Scattered throughout the body, particularly within major blood vessels, chemoreceptors quietly monitor oxygen and carbon dioxide levels within the blood, sending signals that help regulate breathing rate and depth. In the unique atmosphere of a spacecraft, with its particular blend of gases, these receptors gradually recalibrate, adjusting their sensitivity to match this new, consistent environment. It's yet another example of the body's remarkable, quiet intelligence, constantly listening, constantly adjusting, never entirely passive, even in the stillness of space. And this adaptation extends naturally into the lungs themselves. Because pulmonary function changes as well. Without gravity pulling fluid and tissue downward within the chest, lung function shifts subtly during spaceflight. Airway resistance can decrease slightly. The distribution of airflow within the lungs becomes more even, no longer influenced by gravity pulling more heavily on the lower portions, the way it does here on Earth. Breathing itself, in many ways, becomes gentler, more uniform, a small, quiet mercy amidst so much other adaptation. And yet, amid all of these gradual, largely harmless adjustments, one potential risk requires careful, continuous monitoring. Because arrhythmias may occur. With the heart's structure changing, its regulatory signals shifting, and its overall workload reduced, occasional irregular heartbeats have been observed in some astronauts during long-duration missions. Most are minor, and closely monitored by medical teams both in space and back on Earth. But they serve as an important reminder that the human heart, remarkable as it is, remains deeply, intricately tied to the world it evolved within. Space does not damage us, exactly. It simply asks the body to become something slightly different, more suited to a life without gravity's constant presence. And our bodies, patient and endlessly adaptable, quietly comply, reshaping themselves, moment by moment, day by day, in response to a world utterly unlike the one they were shaped for. There is something deeply humbling about it, isn't there? To realize just how much of what we consider normal, our heartbeat, our blood pressure, even the rhythm of our breath, is quietly, invisibly shaped by the very planet beneath our feet. And to imagine, just for a moment, what it might feel like to let all of that gently unwind and begin again in the silence of space. In the next part of our journey, we'll continue exploring just how far this transformation reaches, moving beyond the heart and lungs, into muscles, bones, and the quiet, gradual reshaping of the body over months spent far from home. For now, let your own heartbeat settle into its familiar rhythm. Steady, unhurried, exactly as it should be. We'll continue soon. Let's continue this quiet exploration, moving now beyond the body's adjustment to weightlessness alone, into something far more invisible and far more ancient in its danger. Because beyond gravity, space carries another quiet influence on the heart, one that reaches far beyond simple adaptation. Radiation stiffens arteries. Here on Earth, our atmosphere and magnetic field work together, quietly, constantly, shielding us from the vast majority of cosmic radiation drifting endlessly through space. It's a protection so complete, so seamless, that most of us live our entire lives without ever considering it at all. But beyond that protective shield, in the depths of space itself, radiation exposure increases significantly. And over time, this radiation can affect the very structure of blood vessels, contributing to a stiffening of arterial walls. Vessels that were once flexible, responsive, able to expand and contract smoothly with each heartbeat, gradually become a little less pliable, a little more rigid. Not unlike a process that, here on Earth, often unfolds slowly, across many decades of natural aging, but which, in the radiation-rich environment of deep space, may occur more quickly than expected. It's a sobering thought, isn't it? That the very stars we gaze up at with such wonder, also carry, quietly, invisibly, a kind of accelerated erosion, for anyone who ventures far enough beyond our planet's gentle protection. And this influence doesn't stop at the vessels alone. Because radiation can damage heart tissue directly, as well. The heart, like every other tissue in the body, is made of living cells, delicate, complex structures, vulnerable to the kind of high-energy particles that travel largely unimpeded through the vacuum of space. Prolonged exposure can gradually damage these cells, potentially affecting the heart's structure and function over time. Researchers studying astronauts, particularly those from historic deep space missions, like the Apollo program, have observed patterns suggesting a higher rate of cardiovascular issues later in life, compared to astronauts who remained within the protective shielding of low Earth orbit. It's not a definitive answer, not yet. But it's a quiet, important thread of research, one reminding us just how much protection our planet quietly offers, simply by being where it is. And alongside these slower, cumulative effects, there's a more immediate risk to consider as well. Because in this altered environment, blood clots become possible. With blood flow patterns shifting due to microgravity, combined with the vessel changes brought on by radiation exposure and prolonged inactivity, the risk of blood clot formation can increase during long-duration missions. In fact, in 2019, doctors monitoring astronauts aboard the International Space Station identified a blood clot in one astronaut's neck, a finding that surprised even experienced flight surgeons, and prompted new avenues of study into cardiovascular health during extended time in space. It served as an important, sobering reminder that even in an environment as carefully monitored as the space station, the human body can still surprise us, still reveal new challenges, hidden just beneath the surface of what we thought we already understood. And this brings us to an honest, quietly important truth. Because researchers are still studying these combined effects, even now. Human spaceflight remains, in many ways, still a young frontier, just over 60 years old, when measured against the vast scope of human history. In every mission, every long-duration stay aboard the space station, every carefully monitored astronaut, adds new pieces to a puzzle scientists are only beginning to fully understand. How radiation, weightlessness, isolation, and time interact together, how they combine, compound, and sometimes counteract one another, remains an active, evolving field of research. Not because we lack answers entirely, but because space itself continues to reveal new questions, layered subtly beneath every answer we uncover. And it's not only the heart that changes, out there, far from home. Because gradually, quietly, muscles begin to weaken as well. On Earth, simply existing requires constant effort from our muscles. Standing, walking, even sitting upright demands a continuous, quiet battle against gravity's steady pull, a battle so automatic, so deeply ingrained, that we rarely notice the effort at all. Remove gravity, and that battle simply stops. Muscles that once worked constantly, effortlessly, throughout every single day, suddenly find themselves with far less to do. And muscle, much like the heart itself, responds to reduced demand by gradually growing weaker, softer, less capable than before. It happens slowly, at first. Astronauts describe it less as a sudden loss, and more like a gentle draining, a quiet fading of strength, day by day, even while feeling otherwise completely healthy. And certain muscles, it turns out, are affected far more than others. Because lower body muscles suffer the most. Muscles in the legs, hips, and lower back exist, primarily, to support the body against gravity, holding us upright, allowing us to stand, walk, climb, and move throughout our daily lives. In space, with no ground to stand on, and no body weight to support, these muscles suddenly find themselves almost entirely without purpose. Without regular, weight-bearing use, these particular muscle groups can weaken remarkably quickly, sometimes losing a noticeable percentage of their strength within just a few weeks, if left unaddressed. It's part of why astronauts spend so much time, every single day, engaged in careful, deliberate exercise, not for aesthetics or fitness in the way we usually imagine it, but simply to preserve the basic physical capability to function normally, once they return to Earth's demanding gravity once again. And beneath the surface, within the muscles themselves, an even more intricate transformation quietly unfolds. Because individual muscle fibers begin to change. Our muscles are composed of different types of fibers, each suited for different kinds of work. Some, known as slow-twitch fibers, are built for endurance, the steady, continuous effort required simply to remain standing, hour after hour. Others, fast-twitch fibers, are designed for short, powerful bursts of movement, sudden effort, rather than sustained endurance. In microgravity, where slow, sustained effort against gravity is no longer required, muscle fibers gradually begin shifting in composition, slow-twitch fibers, in particular, becoming less dominant, replaced increasingly by fibers more suited to occasional, brief exertion. It's the muscle tissue itself, quietly adapting its very architecture to better match the demands of this new, weightless existence. And among all the muscles affected by this shift, one particular group changes most dramatically of all. Because anti-gravity muscles shrink the most. These are the muscles specifically responsible for holding us upright against gravity's constant pull, particularly within the legs and along the spine. On Earth, these muscles remain almost continuously active, even during something as simple as quiet, motionless standing. In space, with that continuous demand entirely removed, these particular muscles experience the most significant atrophy of all. Some studies suggest a loss of up to 20% of muscle mass within these key anti-gravity muscles, during missions lasting several months. It's a striking reminder of just how much invisible, continuous effort our bodies quietly invest, simply in the act of standing still. And this transformation reaches even deeper, into the very proteins that give muscle its strength. Because muscle proteins themselves begin to change. Within each muscle fiber, specialized proteins work continuously, breaking down and rebuilding themselves, in a constant, delicate balance that maintains muscle strength and structure over time. In microgravity, this balance shifts. The rate of protein breakdown often begins to outpace the rate of rebuilding, leading to a gradual, cumulative loss of muscle mass and strength over the course of a mission. It's a subtle, molecular-level story, one playing out quietly, invisibly, within every muscle throughout the body, even as astronauts continue their daily work, seemingly unaffected on the surface. And finally, alongside this quiet restructuring, even the way muscles fuel themselves begins to shift. Because fuel use within the body changes as well. Muscles typically draw energy from a careful, adaptable combination of fat and carbohydrates, depending on the intensity and duration of activity. In microgravity, with significantly less continuous physical exertion required simply to move through daily life, this balance shifts as well, often favoring different fuel sources than those typically used here on Earth. Combined with changes in appetite, digestion, and overall activity levels, this shifting metabolism becomes yet another quiet variable, one more thread, woven into the body's broader, ongoing story of adaptation, far from the world it was originally shaped to inhabit. It's remarkable, when you step back and consider it fully. How deeply, how completely, our bodies remain in constant conversation with the world around us, even in ways we rarely notice, day to day. Remove gravity, remove the protective shield of our atmosphere, and the body responds, not with failure, but with quiet, continuous adaptation. Rewriting itself, cell by cell, fiber by fiber, in response to a reality utterly unlike the one it evolved to expect. In the next part of our journey, we'll continue following this quiet transformation, moving from muscle into bone itself, exploring just how deeply space reshapes even the most solid, seemingly permanent structures within the human body. For now, let your own muscles soften, just slightly. Let your body rest here, supported gently by the ground beneath you, a quiet, familiar comfort, so easy to overlook, and so remarkable to finally notice. We'll continue soon. Let's continue, following this quiet unraveling a little further, into the body's own attempts to repair itself, and what happens when even that ability begins to change. Because muscles don't simply weaken in space. Their capacity to heal begins to shift as well. Satellite cells repair less effectively. Deep within muscle tissue exist small, specialized cells called satellite cells, quiet, patient repair workers, activated whenever muscle fibers experience damage or stress. On Earth, they respond reliably, almost automatically, helping muscles recover and rebuild after the countless small strains of everyday movement. In microgravity, researchers have observed that these satellite cells become less effective in their role. With reduced mechanical loading, and fewer of the small, everyday muscular stresses that normally trigger their activity, they simply have less practice, less reason to respond with their usual efficiency. It's a quiet consequence, easy to overlook, but significant nonetheless. The body's own repair system, growing gradually less responsive, simply because it's asked to do so little. And beneath even this cellular response, something deeper begins to shift, within the muscle's own genetic instructions. Because muscle precursor genes themselves begin to change. Every muscle fiber carries within it a complex set of genetic instructions, guiding how it grows, repairs, and adapts to the demands placed upon it. In space, researchers have found that certain genes responsible for muscle development and precursor cell activity shift in their expression, some becoming less active, others adjusting in ways scientists are still working to fully understand. It's a profound thought, isn't it? That something as vast and abstract as gravity's absence can reach all the way down into the quiet, molecular language written within our own cells. Not damaging them, exactly, but rewriting, subtly, the instructions they follow. And yet, remarkably, much of this rewriting isn't permanent. Because recovery genes activate once astronauts return to Earth. The moment gravity's familiar pull returns, the body responds almost immediately, certain genes associated with muscle repair and rebuilding beginning to reactivate, sensing the renewed demand placed upon the muscular system. It's a quiet, elegant demonstration of the body's resilience, not simply accepting a new, weaker state permanently, but actively working to restore what was gradually lost. Still, this process of recovery isn't instant. And it isn't always complete, in every sense. Because nerve muscle recovery may lag behind. Muscles don't work in isolation. Every movement depends on a precise, coordinated relationship between nerves and muscle fibers, signals sent, received, and acted upon in perfect synchrony. After extended time in microgravity, this coordination can become slightly less efficient. Even as muscle mass and strength gradually rebuild, the finer, more precise neuromuscular communication, the subtle coordination required for balance, agility, and fine motor control, can take noticeably longer to fully restore. This is part of why astronauts, upon returning to Earth, often require extensive rehabilitation, not simply to regain strength, but to relearn, quite literally, how to move with the same confidence and precision they once had, before their bodies adapted to a world without gravity's guidance. And even once strength and coordination largely return, a quieter, more lingering vulnerability can remain. Because muscles may become easier to injure, even afterward. Some studies suggest that muscles affected by extended periods in microgravity may remain somewhat more susceptible to injury, even after apparent recovery. Whether due to subtle, lingering changes in muscle fiber composition, connective tissue, or neuromuscular coordination, researchers continue studying this phenomenon closely, another quiet reminder that space's influence on the body doesn't always end the moment an astronaut's feet touch solid ground once again. And while all of this unfolds within the muscles, an entirely separate, equally significant transformation begins as well, deep within the body's very framework. Because bone loss begins, quietly, almost from the very start. Just as muscles weaken without the demands of gravity, bones, which constantly rebuild themselves in response to mechanical stress and weight-bearing activity, begin to lose density in its absence. Astronauts can lose bone mass at a rate significantly faster than even the natural aging process here on Earth, sometimes as much as 1 to 2% per month, particularly within weight-bearing bones like the hips and lower spine. It's a striking thought. That months spent floating gently, weightlessly, through the quiet beauty of space, can, at the very same time, quietly hollow out the very structure holding the body together. And this loss of bone density carries with it another, less obvious risk. Because kidney stone risk rises as well. As bones gradually lose density, calcium is released into the bloodstream in greater amounts than usual. Combined with the body's overall fluid shifts, and changes in hydration patterns during spaceflight, this increased calcium can sometimes lead to the formation of kidney stones, a small, but potentially quite painful complication, requiring careful monitoring and prevention throughout long-duration missions. It's a quiet, intricate reminder of just how deeply connected every system within the body truly is. A change beginning quietly within bone tissue, rippling outward, eventually reaching organs seemingly unrelated altogether. And even the body's fundamental ability to heal bone itself begins to shift. Because bone healing changes in microgravity. The natural, familiar process of bone healing, the way a break gradually knits itself back together, rebuilding structure and strength over time, relies partly on the same mechanical stresses that keep bones strong in the first place. Without gravity's steady pull providing that stress, researchers have observed that bone healing can become slower and structurally different compared to healing that occurs under Earth's familiar gravity. And even once astronauts return home, and bone density gradually begins to rebuild, the story doesn't end quite as simply as we might hope. Because bone regrowth isn't identical to what was lost. Studies suggest that while astronauts typically regain much of their lost bone density after returning to Earth, the newly rebuilt bone isn't always structurally identical to the bone that existed before their mission. Its internal architecture, the delicate, lattice-like structure providing bone with both strength and flexibility, may differ subtly, even after apparent recovery. Researchers continue investigating exactly what this means, long-term, for astronauts' bone health throughout the remainder of their lives. And perhaps most sobering of all, this entire process of recovery unfolds slowly, patiently, never all at once. Because full recovery takes months, sometimes even years. Unlike the relatively rapid loss experienced during spaceflight, rebuilding lost bone density, restoring full muscular strength, and fully recalibrating the body's cardiovascular and neuromuscular systems takes considerably longer. Many astronauts continue physical rehabilitation for months after returning to Earth, and some studies suggest certain physiological changes may persist, in subtle ways, for years afterward. It's humbling, isn't it? To realize just how quickly the body adapts to weightlessness, and yet, how much more slowly, how much more carefully, it must work to return to the world it originally came from. There's something quietly profound in all of this. Our bodies are not fixed, unchanging structures, simply carried through life unchanged. They are constantly listening, constantly responding, shaped, cell by cell, by every environment they inhabit. Send them into space, weightless and free, and they adapt, faithfully, completely. Bring them home again, and just as faithfully, just as patiently, they begin the long, quiet work of finding their way back. In the next part of our journey, we'll continue exploring this delicate balance, moving beyond muscles and bones, into the deeper, more hidden ways spaceflight reshapes the body, the mind, the senses, and the quiet, remarkable resilience carrying astronauts through it all. For now, let your body rest here, held gently, effortlessly, by the quiet, familiar pull of the earth beneath you. A pull so constant, so reliable, that we rarely think to be grateful for it. We'll continue soon. Let's continue, following this long, quiet thread of transformation just a little further, before it leads us somewhere new entirely. Because before we move on, it's worth pausing on one final truth about the body's physical toll. Longer missions leave lasting damage. The changes we've explored so far, in the heart, the muscles, the bones, aren't uniform across every mission. Generally speaking, the longer an astronaut remains in space, the deeper and more lasting these changes tend to become. A short mission of a few weeks may allow for a relatively swift, complete recovery. But missions stretching 6 months, a year, or longer, begin to leave marks that don't always fully fade, even long after returning home. This is part of why space agencies study long-duration missions so carefully, not simply to understand what happens during the mission itself, but to understand what remains afterward. Because as we look toward future journeys, to Mars, and beyond, understanding these lasting effects becomes not just a matter of curiosity, but of genuine necessity. And now, let's shift our attention away from the body's muscles, and bones, and cardiovascular system, and towards something even more intimate. The brain itself. And the quiet, complex ways it too begins to adapt, when gravity no longer anchors its sense of the world. Because almost immediately upon reaching space, many astronauts experience something both mundane and deeply revealing. Space motion sickness begins. Within the first hours, sometimes the first days, of arriving in microgravity, a significant number of astronauts experience symptoms remarkably similar to seasickness. Nausea, disorientation, a subtle, persistent unsteadiness, even while remaining perfectly still. It's not caused by movement, exactly, but by conflict. A quiet, internal disagreement between different systems within the body, all trying to make sense of an environment unlike anything they evolved to understand. And at the very center of this internal conflict lies a small, intricate structure deep within the inner ear. Because the vestibular system itself begins to change. The vestibular system, nestled within the inner ear, constantly monitors balance, motion, and spatial orientation, normally relying heavily on gravity's steady pull to help distinguish up from down, and stillness from movement. In space, with that gravitational reference suddenly removed, the vestibular system essentially loses its primary source of information. At first, this creates confusion. Conflicting signals arrive from the eyes, suggesting one thing, while the inner ear, and the body's own sense of position, suggests something else entirely. It's this very conflict, this quiet neurological disagreement, that often produces those early, uncomfortable symptoms of space motion sickness. Over time, remarkably, the brain adapts. It begins relying more heavily on visual cues, and less on the now unreliable signals from the vestibular system, a quiet, elegant example of neuroplasticity in action. But this adaptation, however impressive, comes with its own quiet cost. Because balance becomes difficult, both during and after spaceflight. While the brain gradually adjusts to weightlessness during the mission itself, this newly rewired sense of balance doesn't always translate smoothly back to Earth's gravity once astronauts return. Many describe feeling remarkably unsteady in their very first hours and days back home, a lingering disorientation, as their inner ear and brain slowly relearn how to properly interpret gravity's familiar pull once again. And this disruption to balance doesn't end simply with standing still. Because walking itself later becomes difficult, too. Something as instinctive, as deeply automatic as walking, relies on a delicate, constant collaboration between the vestibular system, vision, and muscular coordination. After extended time in microgravity, astronauts often require days, sometimes longer, to walk with the same steady confidence they once had. Some describe an early sensation of the ground feeling strangely unstable beneath them, almost as though gravity itself needs to be, quite literally, relearned. And even beyond balance and movement, something even more delicate begins to shift, deep within the eyes themselves. Because vision changes during spaceflight, as well. Just as fluid shifts upward throughout the body, this same redistribution affects the eyes, and the delicate structures surrounding them. Increased pressure within the skull, caused by this upward fluid shift, can subtly reshape the eye itself, sometimes flattening its structure slightly, or affecting the layers of tissue lining its interior. Many astronauts report gradual changes in their vision during long-duration missions, particularly difficulty focusing on objects at a distance. And this change reaches even deeper, into the very nerve responsible for carrying visual information to the brain. Because the optic nerve itself can change. In some astronauts, imaging has revealed subtle swelling of the optic nerve, a condition researchers now refer to as spaceflight-associated neuroocular syndrome. It's believed to result from that same increased pressure within the skull, quietly affecting the optic nerve over the course of extended time in microgravity. It remains an active, ongoing area of research, one of the more significant medical questions facing future long-duration missions. And troublingly, this isn't always something that fully resolves upon return. Because some eyesight problems remain, even after coming home. While many vision changes gradually improve once astronauts return to Earth's gravity, certain effects, particularly related to this optic nerve swelling, can persist for months, or in some cases, remain permanently altered. It's one of the more sobering realities of long-duration spaceflight, a quiet reminder that some of the body's adaptations to space, while remarkable, don't always fully reverse themselves once we return home. And beyond the eyes, something even less visible begins to shift as well. Quietly, subtly, within the mind itself. Because cognitive changes can appear during extended missions. Some astronauts report subtle shifts in cognitive function during long-duration spaceflight, changes in memory, spatial reasoning, or reaction time. Researchers believe this may relate to several combined factors: elevated carbon dioxide levels, sleep disruption, isolation, radiation exposure, and the significant fluid shifts occurring throughout the body, including within the brain itself. It's difficult to isolate any single cause. Space, in many ways, changes the entire environment surrounding the brain, simultaneously and continuously. And the brain, remarkably adaptive as it is, responds to all of these changes at once, in ways scientists are still working carefully to untangle and understand. And finally, even senses as seemingly simple as smell and hearing begin to shift as well. Because smell and hearing change during spaceflight, too. With fluid shifting toward the head, many astronauts describe a sensation similar to a mild, persistent head cold, a subtle stuffiness, affecting their sense of smell, and sometimes muting flavors as well. Meals that once tasted vivid and familiar can seem strangely bland, or different, throughout much of a mission. And within the quiet hum of a spacecraft's continuous life support systems, astronauts' hearing gradually adapts as well, becoming attuned to a very particular, constant soundscape, unlike anything found naturally here on Earth. It's remarkable when you step back and consider the full scope of it. Nearly every sense, every subtle system quietly shaping how we perceive the world around us, shifts, in some way, once gravity's steady influence disappears. Not broken, exactly. Not truly damaged, in most cases. Simply reshaped. Recalibrated, gently and continuously, by an environment utterly unlike anything the human body, or brain, ever evolved to expect. In the next part of our journey, we'll continue exploring this quiet reshaping further, venturing into sleep, mental health, and the deeper psychological experience of living and working so far from the world we call home. For now, let your senses settle, gently, into this familiar place. The quiet weight of gravity beneath you. The steady, unhurried rhythm of your own breath. We'll continue soon. Let's continue, drifting now from the senses into something even more fundamental. The quiet, natural rhythms that normally govern our days, and what happens when the very cues shaping them disappear entirely. Because in space, sleep rhythms themselves begin to disappear. Here on Earth, our bodies rely on something so constant, so automatic, that we rarely think of it as remarkable at all. Sunrise. Sunset. 16 hours of light, followed by 8 hours of darkness, repeating endlessly, day after day, shaping an internal rhythm so deeply ingrained it feels less like a habit, and more like an inseparable part of who we are. But aboard the International Space Station, orbiting Earth every 90 minutes, that rhythm dissolves entirely. 16 sunrises. 16 sunsets. Every single day. Light and darkness cycling so rapidly that the body's natural cues, the ones telling it when to wake and when to rest, simply lose their meaning. Astronauts must rely instead on artificial schedules, carefully designed lighting systems, and strict daily routines, consciously recreating a rhythm the body would otherwise struggle to find on its own. It's a strange, quiet effort, manually rebuilding something that, back on Earth, unfolds so effortlessly, we rarely even notice it happening. And this disruption doesn't remain isolated to sleep alone. Because circadian disruption places stress on the entire body. Our circadian rhythm, often called our internal body clock, doesn't only govern sleep. It quietly regulates hormone release, digestion, immune function, and even our emotional and cognitive well-being throughout each day. When that rhythm becomes disrupted, particularly over long stretches of time, its effects ripple outward, gently but persistently, into nearly every other system within the body. Many astronauts report irregular, lighter sleep during their missions, often accumulating a quiet, cumulative sleep debt over the weeks and months of their mission. And this disruption doesn't remain isolated to feeling merely tired or foggy. It touches something deeper, something quieter, and in many ways, more concerning. Because the immune system itself begins to weaken. Our immune system depends heavily on consistent rest, hormonal balance, and steady physiological rhythms to function at its best. Disrupted sleep, combined with the physical stress of adapting to microgravity, and elevated stress hormones common during spaceflight, all quietly compound, leading to measurable changes in immune function among astronauts. Certain immune cells become less active. The body's ability to fight off infection, or properly regulate inflammation, can weaken during extended missions. It's a quiet, invisible vulnerability, one existing far beneath the surface of daily life aboard the station, rarely noticed until it becomes relevant in a way no one hoped for. And layered atop this weakened immune response, lies perhaps the most invisible danger of all. Because radiation quietly damages DNA itself. Beyond Earth's protective atmosphere and magnetic field, astronauts are exposed to significantly higher levels of cosmic radiation, high-energy particles capable of passing directly through spacecraft walls, and even human tissue itself. At the cellular level, this radiation can damage DNA, the very blueprint contained within nearly every cell throughout the body. Our cells possess remarkable, built-in repair mechanisms, constantly working to correct this kind of damage before it causes lasting harm. But with prolonged exposure, particularly during long-duration missions, the sheer volume of DNA damage can begin to outpace the body's natural ability to repair it fully, raising long-term concerns about cellular health and increased cancer risk that researchers continue to study closely. And this radiation exposure carries other, more immediate risks as well. Because cataract risk rises among astronauts. The lens of the human eye is particularly sensitive to radiation exposure. Studies of astronauts, particularly those who've completed multiple missions, or spent extended time beyond Earth's protective magnetic field, have shown a notably higher incidence of cataracts later in life, a clouding of the eye's lens, gradually affecting vision over time. It's a quiet, cumulative effect, one that may not become apparent for years after a mission ends, yet traces its origins directly back to those months spent drifting through the radiation-rich environment beyond our atmosphere. And troublingly, these two challenges, radiation and microgravity, don't simply exist side by side. Because radiation and microgravity combine, compounding each other's effects. Researchers have found that the cellular damage caused by radiation often becomes more difficult for the body to repair properly while also adapting to weightlessness. The very mechanisms your cells might normally use to detect and correct DNA damage can become less efficient in microgravity, meaning the combined environment of space presents challenges even greater than either factor might create entirely on its own. It's a sobering reminder that space isn't simply one obstacle to overcome, but many, layered quietly atop one another, each interacting with the others in ways scientists are still working patiently to fully understand. And beneath all of this, deep within the body's own genetic machinery, something even more fundamental begins to shift. Because gene activity itself begins to change during spaceflight. Our genes aren't fixed, unchanging instructions, read the exact same way throughout our entire lives. Instead, they can be turned on, or off, or adjusted in their activity, a process known as gene expression, influenced constantly by our environment, our stress levels, and countless other factors. In space, researchers have observed significant shifts in gene expression across numerous biological systems, genes related to immune function, bone density, muscle maintenance, and cellular repair, all adjusting their activity in response to this unfamiliar environment. It's the body, quite literally, rewriting parts of its own genetic instructions, adapting, moment by moment, to a reality utterly unlike the one it evolved within. And remarkably, not all of these genetic shifts fade once astronauts return home. Because some genetic changes remain, even after coming back to Earth. One particularly striking finding emerged from NASA's twin study, a research project comparing astronaut Scott Kelly, following nearly a year aboard the International Space Station, with his identical twin brother, Mark, who remained on Earth throughout that same period. While many of Scott's physiological changes gradually returned to normal after his return, a small percentage of gene expression changes appeared to persist, at least in the months immediately following his mission. It's a profound thought, isn't it? That an experience spanning less than a single year could leave behind traces, quiet and lingering, within the very genetic expression of the body itself. And this genetic reshaping doesn't remain limited to muscles, bones, or immune function alone. Because even the brain's own gene activity begins to change. Studies involving both astronauts and animal models sent into space have revealed shifts in gene expression specifically within brain tissue, genes related to inflammation, neural connectivity, and cellular stress response, all showing altered activity following extended time in microgravity and radiation exposure. It suggests that space affects not only how the brain functions moment to moment, but potentially how its very cells express themselves at the deepest, most fundamental level. And this altered activity, much like the broader genetic changes seen throughout the body, doesn't always resolve completely once the mission ends. Because DNA activity can remain altered long after returning home. Researchers continue to study just how long these genetic changes persist, and what they might mean for astronauts' long-term health throughout the remainder of their lives. It remains one of the most fascinating, and still not fully understood, areas of space medicine today, a quiet reminder that spaceflight's influence doesn't simply end the moment a spacecraft touches down. There is something deeply humbling in all of this, isn't there? To realize that the human body, down to its most fundamental genetic instructions, remains in constant, quiet conversation with the world surrounding it. Send it into space, and it listens. It adapts. It rewrites itself, gently and continuously, in response to radiation, weightlessness, and the profound silence of a world without our familiar rhythms of light and dark. And in many cases, it carries some part of that experience forward, quietly, long after returning home. In the next part of our journey, we'll continue exploring this invisible landscape further, venturing into the psychological experience of isolation, the emotional weight of distance from home, and the remarkable resilience that carries astronauts through months spent so profoundly far from everything familiar. For now, let your own body rest, gently, in this steady rhythm of day and night, a quiet gift, so easy to take for granted, and so remarkable when you finally pause to notice it. We'll continue soon. Let's continue, following this quiet, invisible transformation into a few final, remarkable corners of the body's story, before we turn, gently, toward the journey of coming home. Because even the trillions of microscopic organisms living quietly within us are not untouched by space. The microbiome itself begins to change. Within every human body lives a vast, invisible community of bacteria, fungi, and other microorganisms, particularly within the gut, playing an essential role in digestion, immune function, and overall health. Here on Earth, this delicate ecosystem develops over a lifetime, shaped by diet, environment, and countless small daily influences. In space, researchers have observed measurable shifts within this microbial community, changes in diversity, and in the balance between different bacterial populations. Altered diet, stress, immune changes, and the unique environment of a sealed spacecraft all quietly influence this inner ecosystem, in ways scientists are still working to fully understand. It's a strange thought, isn't it? That even the smallest living things within us, organisms far too small to see, are also, quietly, adapting to the reality of space alongside us. And this adaptation reaches even to the body's outermost layer. because the skin itself becomes more fragile. Many astronauts report subtle changes to their skin during extended missions, becoming noticeably thinner, more sensitive, and more prone to irritation or minor injury. Researchers believe this may relate to several combined factors: reduced mechanical stress from gravity, changes in fluid distribution, and the broader physiological adjustments occurring throughout the body during spaceflight. Some astronauts describe simple activities, adjusting a piece of equipment, or brushing against a surface, causing minor skin irritation that wouldn't typically occur back on Earth. It's a small, quiet reminder that even our most outward, visible layer remains deeply connected to the invisible forces shaping the rest of the body. And within the blood itself, another quiet transformation unfolds. Because red blood cells begin to decrease in number. Researchers have identified a phenomenon now often referred to as space anemia, a gradual reduction in red blood cell count occurring during spaceflight. It's believed to result from a combination of factors, including that early fluid shift toward the head, and the body's initial response of eliminating what it perceives as excess fluid, including, to some degree, red blood cells themselves. This decrease tends to stabilize over time, as the body adjusts to its new equilibrium. But its effects, quiet and cumulative, ripple outward into other aspects of physical function throughout a mission. And with fewer red blood cells circulating throughout the body, something essential begins to shift as well. Because the blood's oxygen-carrying capacity drops. Red blood cells serve as the body's primary transport system for oxygen, carrying it from the lungs to every tissue and organ throughout the body. With fewer of these cells circulating, the blood's overall capacity to carry oxygen efficiently decreases as well. Astronauts often notice this most clearly during physical exertion. Exercise that once felt manageable back on Earth can feel noticeably more demanding during the early weeks of a mission, as the body adjusts to this new internal balance. And this gradual reduction, given enough time, can develop into something with a name we recognize far more easily. Because temporary anemia develops during extended missions. By the time astronauts return to Earth after long-duration missions, red blood cell counts are often measurably lower than before their journey began, a genuine, if typically temporary, form of anemia. It generally resolves within a few weeks to months after returning home, as the body readjusts once again to gravity's familiar presence. But it remains yet another quiet layer, one more thread within this long, intricate story of the body's adaptation and its patient, gradual return. And this return, this journey home, is where our story turns now. Because as remarkable as the body's adaptation to space becomes, coming home carries its own quiet, significant challenges. Because upon return, simply standing can cause dizziness. After months spent adapting to weightlessness, an astronaut's cardiovascular system, blood vessels, and inner ear are no longer accustomed to managing gravity's sudden, familiar pull. In the very first hours after returning to Earth, many astronauts experience significant dizziness simply from standing upright, blood pooling too easily in the legs, no longer efficiently returning to the heart and brain the way it once did, effortlessly, before their mission began. It's often described as a strange, disorienting sensation, the simple, universal act of standing, suddenly requiring conscious effort and careful balance in a way it never had before. And this challenge extends throughout the entire cardiovascular system. Because the cardiovascular system struggles, broadly, in those first days home. The heart, having spent months working with reduced effort in microgravity, must suddenly resume its full, demanding role, pumping blood upward, against gravity's steady pull, throughout every part of the body, continuously, moment after moment. This transition doesn't happen instantly. Many astronauts experience elevated heart rates and reduced exercise tolerance during their first days and weeks readjusting to life on Earth. And the systems responsible for regulating blood pressure moment to moment require a similarly gradual period of relearning. Because blood pressure regulation recovers slowly, over time. Those baroreceptors we spoke of earlier, the quiet sentinels monitoring blood pressure, adjusting circulation instantly whenever we stand, or move suddenly, must slowly regain their former sensitivity after months of reduced demand in space. This process can take days, sometimes weeks, gradually restoring the body's ability to manage blood pressure changes as effortlessly as it once did, before ever leaving Earth. And throughout this entire process of recovery, not every system heals at quite the same pace. Because some systems recover faster than others. Muscle strength, for instance, often returns relatively quickly, particularly with dedicated, guided rehabilitation. Balance and coordination, tied closely to the vestibular system, may take slightly longer. Bone density, as we explored earlier, often requires many months to fully rebuild. And certain changes, particularly within the eyes, and potentially within specific genetic expressions, as we discussed before, may persist far longer still, sometimes indefinitely. It's a reminder that the body doesn't recover as a single, unified whole, all at once. It heals in layers, each system following its own quiet timeline, shaped by its own particular relationship with gravity, and with time itself. And perhaps most honestly of all, recovery, in some ways, remains incomplete. Even after months of dedicated rehabilitation, even after most systems return to something closely resembling their pre-flight state, subtle differences can remain. Some astronauts describe a quiet, lingering awareness, a sense that some small part of their body remembers space, even long after returning fully to life on Earth. It's not something to fear. It's simply part of the profound, remarkable story of what it truly means to leave our home planet, even briefly, and then, patiently, quietly, find our way back to it once again. There is something deeply moving about all of this, isn't there? The sheer scope of what the human body endures, and adapts to, and ultimately, carries forward, simply to allow us the privilege of glimpsing, even briefly, the vast quiet beauty of space. Every astronaut who has ever left this world has carried a piece of that journey back with them. Quietly. Permanently. Woven, in some small way, into the very fabric of who they are. In the next part of our journey, we'll turn our attention toward the mind itself, exploring the deep, quiet psychological experience of distance, isolation, and what it truly means, emotionally, to live so far from everything familiar. For now, let your body rest here, fully supported by the earth beneath you, whole, familiar, and steady, exactly as it should be. We'll continue soon. Let's continue, gently closing this long exploration of the body's quiet transformation, before we lift our gaze outward, toward journeys that reach far beyond where humanity has ever traveled before. Because even after everything we've explored, it's worth acknowledging, honestly, that some questions remain unanswered. Long-term effects may remain, well beyond what current research fully understands. 6 decades of human spaceflight have taught us an enormous amount about muscles, bones, the heart, the brain, and the countless quiet ways the body responds to weightlessness and radiation. But most of what we know comes from missions lasting months, not years. As future missions stretch longer, toward the Moon, and eventually Mars, science will continue learning, quietly and carefully, what those longer timelines truly mean for the human body over time. And this leads us to something worth acknowledging plainly, rather than glossing over. Because researchers still don't fully understand every interaction at play. Radiation, isolation, disrupted sleep, fluid shifts, reduced gravity, altered immune function, each of these factors influences the body on its own. But they don't occur in isolation. They layer together, continuously, compounding and sometimes counteracting one another in ways still being carefully untangled, mission by mission, study by study. Space medicine remains, in many ways, a young and evolving science, humble in the face of just how much remains to be discovered. And with that honesty in mind, let's turn our attention now, outward. Beyond the relative safety of low Earth orbit, where the space station quietly circles our planet, and toward the deeper, more distant reaches of space that future explorers may someday call their workplace. Because beyond this protective zone, radiation becomes significantly worse. Low Earth orbit, where the International Space Station resides, still benefits from a measure of protection, nestled partially within Earth's magnetic field, which helps deflect much of the most dangerous cosmic radiation. Venture beyond that boundary, toward the Moon, or further still, toward Mars, and that protection largely disappears. Radiation levels increase substantially, exposing astronauts to a far harsher, far less forgiving environment. Which is why, quite simply, Moon and Mars missions carry significantly greater risk. Longer mission durations mean prolonged radiation exposure. Greater distance means slower, more complicated emergency response, should something go wrong. And the deeper physiological changes we've explored throughout tonight's journey, in the heart, the bones, the muscles, the brain, may become more pronounced, and potentially more permanent, the longer humans remain beyond Earth's protective embrace. And here, we must be honest about something important. Because human data, for missions of this length and distance, remain genuinely limited. No human being has yet spent more than roughly a year continuously in space. No human has yet traveled to Mars, experiencing months of transit through deep space, followed by extended time on the Martian surface, then the long journey home again. Much of what scientists currently understand about deep space's effects comes from shorter missions, combined with careful extrapolation, animal studies, and simulations here on Earth. The full picture won't be fully understood until humans actually attempt it. And within that uncertainty, one thing does seem increasingly clear. Because overall risk depends significantly on mission duration. The longer a mission extends, the greater the cumulative radiation exposure, the deeper the muscular and skeletal changes, and the more significant the psychological toll of isolation and distance from home. A journey to Mars, potentially lasting 2 to 3 years round trip, represents a fundamentally different challenge than even the longest missions attempted so far aboard the space station. And interestingly, this risk may not affect every astronaut in quite the same way. Because men and women may respond somewhat differently to these challenges. Emerging research suggests subtle differences between how male and female bodies respond to certain aspects of spaceflight, including radiation sensitivity, fluid shifts, and cardiovascular adaptation. These differences remain an active, ongoing area of study, and understanding them fully will play an important role in preparing safely and effectively for future long-duration missions, ensuring that every astronaut, regardless of these differences, can journey and return as safely as possible. And facing all of this, radiation, isolation, distance, uncertainty, one solution stands out as particularly essential. Because advanced shielding becomes essential for deep space missions. Engineers and scientists continue developing new materials and spacecraft designs, specifically intended to better protect astronauts from cosmic radiation during long journeys beyond Earth's protective magnetic field. From specialized hull materials, to strategically shielded sleeping quarters, to entirely new approaches to spacecraft design, much of the groundwork for future deep space exploration depends on solving this quiet, invisible challenge first. And alongside these engineering efforts, researchers are exploring solutions from an entirely different direction as well. Because scientists are actively studying protective compounds, too. Beyond physical shielding alone, researchers are exploring medications and naturally occurring compounds that might help protect the body at a cellular level, potentially reducing radiation damage, supporting DNA repair, or helping preserve muscle and bone density during extended missions. It remains an evolving, hopeful area of research, one small piece of the much larger puzzle humanity continues solving, patiently, as we prepare for journeys further from home than ever before. And so, we arrive now, at the quiet end of this long, winding journey. Back to the question that first carried us into tonight's exploration. What does it truly mean to float forever in space? Floating forever sounds peaceful, doesn't it? An image of stillness and silence, and endless gentle drifting beneath a canopy of stars. And in some ways, it is beautiful. There is nothing quite like it anywhere else in human experience. But as we've discovered together, tonight, the reality beneath that peaceful image is far more intricate. Far more remarkable. Space doesn't simply hold the body suspended, unchanged, in perfect stillness. It reaches into nearly every part of us, the heart, learning to beat differently. The muscles and bones slowly softening without gravity's quiet demand. The brain and senses recalibrating themselves to an entirely new reality. Even our genes, our very DNA, quietly rewriting small pieces of themselves, in response to a world utterly unlike the one that shaped us. And even when astronauts return, even when they feel, once again, the familiar comfort of solid ground beneath their feet, some part of that experience remains. Quietly. Permanently. Woven gently into who they now are. Perhaps that's the deeper truth hiding within the idea of floating forever. Not that the body remains untouched, drifting eternally through empty stillness, but that it changes, patiently and completely, shaped by an experience unlike anything else on Earth, and carries some part of that transformation forward, for the rest of its life. There is something quietly beautiful in that thought. That to leave this world, even briefly, is to be changed by it forever. And that even here, safely on Earth, held gently by the gravity we so rarely think to appreciate, we remain connected, in some small way, to that same vast, silent universe stretching endlessly above us. Tonight, we've traveled far. Through the science of floating, and falling, and drifting endlessly through the dark. Through the quiet, hidden ways the human body listens, and adapts, and changes, when it finds itself somewhere it was never quite built for. And now, as this journey gently comes to its end, let yourself rest here. Held, softly and completely, by the earth beneath you. Breathing slow. Steady. At home. Wherever you are tonight, you are exactly where gravity intended you to be. Rest well.